I'm Michailidis. Nice to meet you. Thank you for coming. I work as manager of data science at dunnhumby, and I would like to talk with you about my journey in getting to first in Kaggle. Obviously, this is linked a lot with model stacking, which I'll go through in details later on. But it all started from here, so I think it's nice to give a talk, where it all started. I'll tell you a little bit about what Kaggle is. I presume most people should know, but I think a good way to describe it is it's the world's biggest predictive modeling competition platform. So what happened is you have lots of members, like more than 500,000 members right now. And various companies like Microsoft or dunnhumby will host different modeling challenges where they will supply a set of data and they would like to find answers, which are outsourced to lots of people who try to get the best solution. For example, dunnhumby will try to predict when a customer will visit a shop, or Microsoft will try to find which virus has infected a certain file. So all very diverse, all very interesting problems, all can be solved with machine learning. I give you a list of different challenges that are common, but I don't want to go much in detail at this point. I'll come back later. So let me tell you a little bit about how I started with Kaggle, because I think it's you might find it inspiring. I found it inspiring. So I'm originally from Greece, so I came here 6 years ago to do my master's in Southampton, and I remember that at the end of the year I studied risk management. At the end of the year, I was trying to find what to do next. So I used to attend this entrepreneurship type of talks where people tell you about ideas for business. And there was this guy, his name escapes me right now, that he presented his business idea. After he finished his studies, he started going to the horse races, but he wasn't betting, he was collecting data. He was collecting all sorts of data, like weather conditions, like who has won the next X number of races, where do people bet the most. So anything you can think of, he thought of various sort of features that he was monitoring on a daily basis. And he was able to make a predictive model that, it gave him more than 50% to get the winner. And he made lots of money with it. I think the point was it seemed like a superpower the way he explained this. So I thought, yeah, it's kind of cool. I want to do this. So this is actually how it started. So I was really curious. Back then SaaS SPSS were dominating the market. So if I wanted to learn about algorithms and tools, I had to invest in this. Over time, and as I became more passionate, I felt that I have to dive deeper. So I have to be able to code these things myself. I had zero programming experience by that point, so my background is economics and then risk management. But the most I have ever done was like some functions in Excel. So I picked up some programming skills. I specifically started with Java, and the reason I started with Java is because I started with C and I found it was too difficult. So then I said, maybe Java is better. But I think later also I picked up Python, and it was quite a nice transition because Python is in a way easier. But yeah, I started learning a lot and I started coding a lot. And then once I built lots of algorithms, I tried myself basically to deal with different sort of problems. Then I decided to package everything and make it available. So I created a tool which it's more like a GUI to be used for simple credit scoring applications. You could say simple analytics applications, and it contains lots of algorithms, and I named it Casanova, The name comes from ANOVA, which is, it's analysis of variance. And the suffix, the prefix is Casani, which is my mother's last name. The idea of the logo is that you see the nose is quite big, and you have to be nosy with the data in order to get the most out of it. That was the idea. My sister made the logo. I tried to include all my family into this. Maybe a typical Greek thing. And then, actually, before I joined Kaggle, I joined dunnhumby. And at dunnhumby, I found out that they had already hosted 2 Kaggle competitions right at this point. They were trying to solve different problems, and people were talking a lot about it. So, I thought that I should upskill myself to see what exactly is that and how I can reach that level. So I started with a few competitions, and I guess initially I didn't do very, very well, but it didn't seem like I wasn't doing very well, because I was learning a lot. But I think that's the point. It never felt like. It didn't stress me. It was really nice because people were really open. They were sharing stuff. There was a lot of collaboration, and I've learned lots. And over time, I think after 100 competitions, I sort of also found a way to be able to do consistently well. But yeah, I do want to highlight the fact that sharing and collaboration is great, and therefore I encourage everybody to give it a shot. So I think the end results of me playing 3 years in actively participating in Kaggle competitions is I have played in more than 100 different very, very diverse challenges in certain situations. I have teamed it a lot, so in about half of my situations I have collaborated with different teams from different nationalities, different ages, completely different backgrounds, data scientists, engineers, biologists, lawyers, even sometimes you might find it strange, but they wanted to make a transition. It's data science is a hot topic, so I had a couple of top 10 finishes. obviously it didn't happen immediately. It took some time to develop sort of the pipeline that can get you there, and a lot of reading and a lot of collaboration, but eventually I got there. Prize winner a couple of times. I have not participated only in Kaggle. There was a period where Kaggle was not enough, but I think right now it is. It was at some point I was really so eager. I was participating in everything that there was out there. I think the end result of all of this is at some point I managed to get first in the global ranking list. The way it works is that with every competition, based on how many points you get, based on the position you get different points. It's almost like in tennis, if where the more you participate, the better positions you get, the more ranking points you're awarded. So there is this sort of league. So after 3 years of competitions, I managed to get first. You may see the Greek flag there, just because the moral of my country is quite low at the moment with all the financial crisis. So I thought I should give it a boost. So I think, and now I'm slowly getting into the more interesting part for you. What wins competitions? In a very rough summary, I think first of all you need to understand the problem. You need to understand what you try to optimize. You need to understand what you try to predict. You need to understand, like the data that you have. Do you have dates? Do you have categorical data? Do you have numerical data? Do you have data which are very specific to the kind of problem you're solving? All sorts of things. You need to really spend some time to understand what you're trying to solve. I can give you an example. I remember there was an insurance competition where you had to predict which policy customers will pick, but you would see that in 99% of the situations they were renewing. They were just picking the same policy. So actually there was no it was more valuable to try to predict if they will renew or not, rather than trying to find immediately which policy it is, and sort of map this into a two-stage problem. So I mean, this kind of thorough investigations of the problem can really help you to break it down to smaller ones, and just helps you get better solutions. I think you need to have discipline, especially in how you test. Kaggle has a leaderboard where you submit your scores and you can sort of see how well you've done. However, in most situations, what determines the winner from the loser, if there is such thing as a loser, is how well you've managed to replicate that testing environment internally. So if you manage to create a test environment internally which is very reliable, you can try all sorts of things without being afraid. I mean, you can explore lots of possibilities, or if every possible permutations or combinations of your data. And you need to be very strict with that, because it's easy to make models which are not generalizable, or they underfit, or as they use the term, overfit. So you need to follow a certain strict guideline about that defines model selection, hyperparameter optimization, and all these things used in modeling. You need to try problem-specific things. I mean, unless you try convolutional neural network, I guess, with the previous Atari example, it was probably not going to do very well. It is the same with image classification. I think unless you really try what's state of the art right now, you're not going to perform competitively. And I think that's the mentality you need to have for every problem. It's good to have an idea at least about what solves it best, and have the tools, which is the next thing I wanted to say. You need to have access to the right tools. This means hardware, this means software. You need to always be up to date, have all the latest releases, all the packages, and the right packages. And always put the time and the hours to try new things. I remember that in that stretch where I managed to get first in Kaggle, I was putting something like 60 hours per week on top of everything else I was doing. So I was insane. Not good for my health. I think collaboration is very important, because apart from the fact that you can sort of divide the space of work you need to do, everybody can focus where is more skilled or more talented at. There is also an element of everybody can see the problem from different angles, may see things that you don't see. So I think in that sense, collaboration, I mean, apart from any other obvious benefit, which is makes it more interesting, more fun, is also it definitely helps performance. It's almost as an ensemble of different approaches, as I will come later to focus on. And ensembling refers to how we combine many different models to get sort of a better result, or how to create a very powerful model by using smaller or weaker models. And I think mastering this is what really, I think, gave me the edge in most of the competitions. And I'll get more details into this later on. So what I'm doing after Kaggle, well, or along with Kaggle, it's not like I have stopped, but I'm not participating as much as in the past. I'm doing also my PhD at UCL about using ensemble methods to improve recommender systems, which is sponsored by dunnhumby. And as part of this, I have developed Stacknet. Stacknet is a methodology to use meta-modeling. It is the same methodology that I have used in Kaggle and have won multiple competitions. And I'll tell you more about it now. So what is Stacknet? Stacknet is a meta-modeling methodology. By the term meta-modeling, I mean that we use other models, in a new model. So it is an after modeling phase. Is a new modeling phase. that it uses Wolpert's stack generalization. This is basically model stacking. Not sure if you've heard the term. It is basically a way to combine different generalizers, let's say different algorithms, to make a stronger model. But I do so in a neural network architecture, where you build multiple models, but in different layers, where the output of each model becomes an input to a new model. And you keep doing that until you squeeze any sort of information there is in regards to your target variable, whatever you try to predict. However, there are various elements into this that we'll go in detail later on. But you can imagine it as a neural network where each node, instead of being a simple perceptron, as it is in, let's say, normal neural networks, here is any machine learning algorithms. It can be any complex function. When I say complex, not as in mathematics complex. I mean non-linear, linear. This is what I mean, complicated. The first version of Stacknet, which is a methodology, but there is also a software implementation with it, which seems it is already working quite well, although it has some. It has only a few algorithms for the moment, for people to play with. But yeah, it is in Java, and I'll tell you now more about the inspiration behind it. So as I mentioned a few elements before, the first was stack generalization. So Wolpert in 1992 introduced stacking. In very simple term, stacking involves 4 stages. First, you have a training data set and you divide it into 2 parts. Then on the first part, you train various algorithms and you make predictions for the other part. Then you take that other part and you have the labels also, the correct answers for that part, and you train a new model where the predictions of the previous phase are now inputs to that new model, and you can retrain it to these labels. This is basically how it works. The predictions on that second data set now form a new data set where with the labels for that hold out data set, you can now train a new model. And this is how it works. So it can be seen also as a way for you to correct the errors of the algorithms, of the predictions of your algorithms that you have already used in a way. The second inspiration is neural networks. Neural networks actually have been here for a while. I think Rosenblatt was the first that he created the perceptron, a very simple, you could say a very simple neural network. Then for some period of time they have almost been dead. Then backpropagation came back into the mix, and perceptron took its revenge for a while. Then I think then the computational requirements to be able to make these models very predictive were not there. But now with the advent of this, with the usages of GPUs, we have sort of come into a stage where we can revisit them and make them deeper, make them more predictive. And I think they have re-emerged right now as being, for many problems, again, the state of the art in predictive modeling. And it is this kind of architecture that, it has various advantages, and that's why I'd like to use it through the stacking mechanism, because as you can see, it's very easy to build models scalably. And by reusing the information in multiple layers, you can squeeze more and get a better prediction. I built that first version of Stacknet in Java. People ask me why Java and not either C, which is more efficient, or Python, that is easier and will have more integration with other algorithms. It's not C because C is, I think it's not very easy to use. It's not easily used for data scientists in the data scientist workflow. just because it is so verbose. I mean, Java is also verbose, but it's not as verbose. I think it's quite easy. I personally find it easy, for example, to work quickly in Java, even for something like a Kaggle competition. I should say that in my first 2 years of competing in Kaggle, the first competition, I won them fully in Java with my own tools. So it's not as easy as Python, but it's definitely easier than C. Yeah, every operational system has it, and this, I think, it's an advantage because you build something and you know it can scale to. It's you know, it has a very big reach. It is statistically typed. I think that's good for, you know, when you really want to build a nice software application. Especially me, the way I code, I'm very prone to making mistakes. So this ensures that I don't. Java doesn't have something like scikit-learn, and I think what I had in my mind when developing this tool, which Stacknet is a part of it, the algorithm it contains is another part, is that it can actually be used in a similar way. You can have a similar API, and you know, people that would like to use Java, they can focus on using this. It has good predictive algorithms. So that was and some basic data pre-processing steps. More will be added on, but that was the idea. So how it works in imagining neural network, where basically each one of the neurons, it can be described as a regressor. So basically as a perception. So is some betas along with a bias. So it's almost a combination of regressions. So here we just replace this with any modeling function. So this can be any, so the way you combine all your input data of the previous layers doesn't have to be linear. It could be a random forest, it can be a gradient boosting machine, it can be anything you want basically. And to just give you this, so instead of going from a linear regression, we just say we replace it with any function. If you want to see it more visually, you can see it like that, model 1, model 2. So in the first batch of models, this is what I have created. This has been created from scratch. So it doesn't rely on any other implementation. It's just pure Java code based on papers or other implementations. How the training works, I think this is the interesting part, because in a traditional neural network, you normally have something like back propagation in order to train it. Here, you can imagine that a neural network, it's very easy to overfit even the way it is. So much more if you have stuff like random forests and gradient boosting machines and all these algorithms combined together. So I haven't massively personally explored this, but I would say it's extremely difficult to apply the same neural network logic in a network where you can put any machine learning algorithm. So this is where stacking really comes into play. So and something before I go into this, I'd like to tell you a limitation of Wolbert, the way he described it, the way he described stack generalization is that you have to divide your dataset into two parts. However, that means that if you want to keep doing it, you will always need to divide your data into two parts. So if you wanted to potentially combine algorithms in multiple levels, you will always need to run your models in much less data. So, and this is a problem, because you can see, you will see, I mean, when you try that, you do get uplift by adding more layers. Obviously, you get more in the first layers, but you can keep getting. But if you make the data too small, then you just can't get any significant results. So here it uses a reusable, Stacknet uses a reusable holdout mechanism. Don't confuse this term with, I know this term has been used somewhere else, but for something completely different. I just noticed recently. So what I mean here is that we have some training data, and what we do is we do k-fold. So let's say we divide it into 5 parts. And we combine, let's say, for 5 times, we combine, if we assume that we're doing a 5K fold, this 5 is a hyperparameter, we use 4 out of 5 of these parts to train and model, and we make predictions for the 5th one. We do that 5 times so that we always predict in a holdout fashion. We always predict, we try to make certain that, make predictions on test data. In a way, so test data. So our predictions are biased. And when we score everything, we just put it back together and we bring that prediction forward. This is how basically the mechanism, it works. And it works really well in practice, like it doesn't overfit as long as there are not very strong temporal elements in your data. So you have very past data predicting very future data. You have, I think there are many ways where you can do the training, but for now I have included 2 modes. One is exactly like a simple neural network. You build the first layer of predictions, then you go to the second layer and you use the previous layer's output as predictions in the new model, and so on. However, as explained earlier, here you don't have this notion of convergence like you have in neural networks, where you have multiple epochs. Every model is immediately trained on your outcome variable. So if you wanted to revisit the initial data, a good way to do it is to actually restack everything. So when you are in the 3rd layer, don't include just the previous direct previous layer's predictions, but also everything else, even the input data, if it may be. And it works well in practice. In many situations, this actually performs better, because allowing an algorithm to seize the data again, it can, it may find some information it didn't find initially with the help of some other models that already help it to explore some part of the information that was already in there. So you have available these 2 modes, and it may be, one or the other. In various Kaggle competitions, it has been one that worked better. In other Kaggle competitions, for example, it has been the other one that worked better. So there are other modes, but I think Stacknet actually comes with this too. Now I would like to talk to you a little bit about the actual implementation, about the software and how it can be used. And later I'll give you an example with some code of how you can use it to get a top score in a Kaggle competition with code in GitHub. The algorithm has, the software package has some commands, so you can run it from the command line. The vision is that later it will be a GUI, so you will have a graphical user interface, but for now it's just a command line. So you have, normally what you need to specify is just a train and a test file. This is my training file, this is my test file. It expects the first column in your training file to be your target variable, so what you try to predict. Then you have various options, like how many folds you want to use for cross-validation, obviously a seed for randomized procedures to be able to replicate the results. If you want to use restacking mode, it is this stack data command. The metric you want to monitor, for now it supports only 4. More will be added. How many models you want to run in parallel. So imagine that the stronger machine you have, the more models in each layer can be run in parallel. And you can also add threads to these models individually too. So you can run in parallel 2 random forests where each one builds some trees in parallel. So you can make your own, you can leverage the most, your cores, you can allocate your cores optimally. Some other details, generally Stacknet supports both sparse and dense data. I don't know if people are familiar with sparse data. Sparse data is when you try to not to list the zeros in your data. So you keep only the non-zero values. Extremely useful for where you have a lot of dummy variables, for example, lots of binary features. So you only keep track of the non-zero ones. Also, Stacknet requires a parameter file. The parameter file looks like that. It's normally a txt file that says you have a break line to determine the levels, and then you list the models that you want to add, each with their hyperparameters. For example, I want to build a Stacknet that has 2 levels. In the first level, I want to have a logistic regression that uses regularization with c-value of 2. I want to use a gradient boosting forest classifier that has these trinkets and has that many estimators. I want to use a random forest. Then I want the outputs of these models to be fitted on a random forest classifier with 1,500 trees. So this is what it looks like. And then you just run a train command. You set the parameters file, you set the train and the test file, and it produces the probabilities, your predictions in that pred __ file. However you define that. It is as simple as that, or not simple. I don't know how you find it. Now I want to get you through to an example that I finished a couple of hours before I came here. So previously I mentioned that I started Kaggle 4 years ago, and initially I didn't do very well. So this was the very first competition I joined. It was a competition hosted by, the sponsor was Amazon, and what they wanted to do is, based on some categorical data, you had to predict whether a certain employee will be granted access, some sort of access, for example administrative rights, or ability to look at transactions based on features like who is your manager, what is your role in the company, what is the kind of resource you ask permission for, this kind of features. And I'll with a little bit of work, with a little bit about less than 2 hours computing time, you can get a top 10 score in this competition. Using Stacknet and a little Python code that I'll show you. How I ran these experiments. This was a popular challenge back then. When I first joined, there were 1,700 team. I finished something like 100 after spending 3 weeks. Now I spend more like, well, I spent 2 days. I spent 2 days, but I didn't. I spent 2 days because I wanted to make certain it looks okay, but I think I could do it much faster. This can get you to a top 10 score within a few hours. I think what was really interesting about this competition is that it has only 8 variables, which you will think, how difficult can it be? Just 8 variables. Actually, you will see huge differences in the scores, and that's because all variables are categorical and they have extremely high cardinality. So they have like thousands of categories. So it is a battle against underfitting and overfitting, how to find, which categories to keep. And obviously you need to explore lots of different interactions in this data set to be able to do well. I remember, I have to admit, I was cocky when I entered in that competition, but I learned my lesson quickly, because I said 8 variables, how difficult can it be, but it was quite tough. I managed to finish around 100, but after reading a lot in the forums and after and after receiving a lot of help, like from the competitors. Yeah, and that's why I recommend Kaggle. This is where I really found out. Actually, all these hours I've put developing software and learning algorithms, when tested in an environment with so many skilled people, I think you can understand, where you need to be. As I said, this kind of problem, you have to predict whether an employee will be granted access. You had to optimize area under the ROC curve. I hope people are familiar with it. Otherwise, it's just a metric that says, that you try to have high correlation between your prediction and the target variable. So the higher the score, the higher truly the probability of a person to be granted access. In order to run these experiments, you need to download the data from that competition. Hopefully we'll share the link, the PowerPoint later, so you can actually try that yourself if you want. And you can see that a detailed example in the Stacknet's official GitHub repo. The way initially you need to prepare the data set. So you need to run a Python script where it produces several files for you, modeling data sets, where then you feed into Stacknet. The way I made this is I built 2 different Stacknets, just because I wanted people to understand the different sort of options they have. The first Stacknet uses sparse data. So what I did is I put these 8 variables and I created all possible 4-way interactions. So variable 1 plus variable 2 plus variable 3 plus variable 4, then 1, 2, 3, 5, then 1, 2, 3, 6. So all possible 4-way interactions, up to 4-way interactions. But I did it in a sort of in a forward manner. So I estimated AUC in cross-validation. Then I added an interaction. I repeat the same cross-validation. If the score is better, I'll leave it in, else I remove it. This is sort of to keep only the important ones. It's a brute force forward way interaction, let's say feature selection. And I use logistic regression to do that. So then the output comes out as a sparse file. So what I do is then of all these interactions, I did something in Python called one-hot encoded. So every feature in these interactions, so every value in these features becomes sort of a binary feature, 1 or 0. Is this role present, 1 or 0? Is this combination of role and role family present, 1 or 0? So this created, I think, something like 500,000 columns. So unless you find a way to compress this data, you cannot really run model on. In reality, most algorithms ignore the 0 elements. So they are only interested for when something is present. So for when something has the value of 1, not for when has the value of 0. So this is what sparse data do. So they only keep the 1 values. But I'm just explaining because I don't know whether you're familiar with it. And once you produce the sparse files, which they follow something called SVM Lite format, then you can run this command. Now it may sound a little bit intimidating by the look of it, but the first line says I want you to run Java and you allocate 3 gigabytes of memory. This is my train file, then this is my test file. I have a parameter file with 9 algorithms. I'll show it to you later. And produce an output prediction file as Amazon linear pred. Use 5 false cross validations. My data is sparse. Just use 1 thread here. And a seed and monitor AUC at each step. So this is the performance of these 9 models I selected. So I have some logistic regression. libfm is very good. So factorization machine is very good for this problem too. Some neural networks and gradient boosting. So you can see the AUC of these models. And I selected a random forest for a level 2 classifier, so to fit on the outputs of every other model. And it scored an AUC of 0.901, which is about a point better than the best model of the previous layer, which was logistic regression with L2 regularization. And generally, this is what stacking does. I mean, it doesn't do magic. It can give you a better result than your best single model, but you know that boost. obviously, this is a factor of many things like diversity, how correlated the models you have created in the previous layer are. But it can give you the edge, especially in competitions where you try to win by yes.
Sorry for interrupting.
No.
But how do you know that you should stop developing the logistic regression model there and you should move towards to the next level for the stacking?
That's a good point. We don't. So you just the way I build it is first I choose only one model, and I run and I check the cross validation, and this is how I tune it. So and then I select the second model. Obviously, you can think of that the more models you add, the better performance you're going to get, and you would hope that even if you add some redundant models, then your second layer model will be able to find it. But there is no way to know that I should stop here. So the way it works is the more, the merrier, and you can hope that you can discard some later on in the meta modeling phase. So this is automatic, but you can also impose some manual elements into it. For example, Stacknet can help you output all the predictions of the previous layers. So you can even check yourself whether I should stop or add more models. But in general, there is no way to find what is the right architecture. There is no way. I mean, in most situations, the more you add, the better it is. And at some point, it converges. You see at cross-validation that you cannot improve anymore. There is no mathematical easy way to determine that there is no more, here you should stop. You cannot add any more value. So the more you add normally, the better it is. I think we can have questions later on, right? So do I have time? Okay. Okay, that was the best performing model. Just a little bit how actually the output looks like. It's just it's a little bit ugly right now. So you have the command in the command line. Then it tells you I've loaded the data. The data is sparse. This is how many elements it has, etc. And then it starts there to give you the results of each one of the models for each one of the faults. And this is also how you tune them. So initially you just look at the results there and you try to get as best HUC as you can per fault for each model. The second experiment actually uses dense data this time, but the difference with the previous one is that here we actually provide the faults ourselves. So previously you provided the file and you said you do the cross validations internally. Here you're actually, we are going to supply 5 different pairs of training and validation data for Stacknet to use. The reason we do this is sometimes we need to make certain that we need to create some features within cross-validation. This is common, especially in Kaggle we use likelihood features or weights of evidence, if you've heard, commonly used also in credit. But these features are not safe to be created in the whole data. These features, it's better to be created through cross-validation. So this way, sometimes it's not easy to run Stacknet unless you create those features yourself. So this is just a different way for you to run Stacknet on your own faults. But here you are responsible yourself for controlling overfitting. So for this dataset, I found all different ways, all different 3-way interactions, but I did no feature selection. And I used the counts of each one of the categories and also created these likelihood features so that each category could be represented with the score that reflected on the target variable, like what's the probability of being granting access. You run these commands. What is different is that you have this data prefix command here, the second line, which actually says we will supply our own faults here, our own pairs of training and test data. And because we have specified 5 faults, this will expect 5 files of Amazon counts, train 0, then train 1, then train 2, then train 3, and train 4, so that you can run the static manually. Here you get this. Here I had a different selection of models. In this type of data, gradient boosting performed the best, but the models were more correlated with each other, so the actual boost we got from the level 2 meta classifier is actually smaller, is only 0.4. But in general, this model is stronger than the previous one. And then what I did, I took these 2 predictions and I blended them. I just submitted on Kaggle. You can run this example and you will get that top 10 score, and there's a lot of room for you to actually go get the top spot. I think you have all the tools you have to do this, but I'll leave it up to you if you want to do that. I think some things you need to be careful is, what you need to know is that Stacknet is not magic. I mean, it may sound like it, but it actually gives you a little bit better results than your best sort of single prediction model. And normally, most of the times, it also does better than any other ensemble method you have, like averaging or voting. It will perform better. At least better enough to win Kaggle competitions. Sometimes it has also great value in real life. Sometimes the uplift is small to be considered. Let's say to be considered at least for large-scale applications. Stacknet may underperform when there are strong temporal elements. I think when I say strong temporal elements, when you have past data and you have to predict very future data, because Stacknet squeezes so much information out of your target variable, it might overfit your training data, no matter how well you may have done your cross-validation. So it may be that you need to do your striking very manually when it comes down to such a problem. Possibly only do one split where you will make certain that the validation data is a lot in the future. You need to sort of try to recreate the same conditions you will be tested on. And when you are supplying your own file, so the second experiment, you need to be you are responsible for controlling overfitting, so you cannot blame Stacknet if that fails. You need to be very careful not to have cases overlapping between training and validation data, and generally not have information in your validation data that you wouldn't normally have in a real testing environment. Stacknet has already been used in some challenges. It has actually won the a competition hosted by Data, which you have to crawl basically websites in order to find whether they contain some sort of advertising or not. So it was more like a text classification problem. And this was the first time I used the term, and since then it remained. It was also used to win the home site conversion challenge on Kaggle, and I released the software now in a competition sponsored by 2 Sigma, and also in Kaggle, and people have reported that a lot of people in the top 10 have reported that they're using it, and it gives them good scores. It's a little bit the same. I released it because the point I did it, everybody passed me on the leaderboard. I can give you a visual example of how stacking was for that data competition. So we built 4 layers where we had 2 different input data similar to what I described before, and then from each layer we keep building models until we reach 4 levels, and it gave us enough boost in order to win this competition. You can see it more analytically later on. What I plan to do next for Stacknet is, for now, Stacknet has some implementation of algorithms which I developed. I would argue they're the most efficient. So what I want to do next is to make certain that it contains the top tools. So when you build your ensembles, you can choose any of the tools you like or love. It has to be accessible in other languages too. Right now it's just a Java tool, but I'll try to make a wrapper for Python, possibly R, so that more people can use it. For now, it's just the modeling part, but in the future I would like to have some at least basic feature engineering steps, convert categorical variables immediately to different formats, counts or one-hot encoding, possibly explore some interactions for some linear models. Hyperparameter optimization, now you do that very manually. However, it is fairly quick because you can resubmit and see your results, but ideally, I don't believe completely automated hyperparameter optimization is possible, to be honest, but I think you can at least have some good some decent initial values. Some feature selection too. Now there is no feature selection, and I would like to extend that into model selection too. So which comes back to your point. After we produced a lot of models, hoping that we can converge, then we can also have a phase where we can make most of the ones that are redundant, disappear. We can refer to this as dropouts too. And I would like to close this with a couple of more tools that I would like to include. Some of them already mentioned, but also my favorite tools in Kaggle. I don't want to go into much detail. Scikit is really good. It has pretty much everything. For gradient boosting, I like XGBoost. LightGBN developed by Microsoft is extremely fast. I think recently I found out that it's actually performing better. Vapal is extremely good for fast linear models. I found it very, very useful for some competitions that had like billions of data. LibLinear also very quick and very efficient for linear models. The original libfm, very good. Also libffm, so field-aware factorization machines. They have been extremely good at clickstream type of problems. Weka in Java has a lot of tools. GraphLab 2, although I'm not sure whether they are still open source. I like open source. Keras and Lasagne, I really like them. To be honest, I don't like personally working directly with TensorFlow or Theano. I'm lazy, so I prefer to use something like Keras that makes it easy for me to construct my neural networks. And when I have tasks that are specifically for ranking, so I have a list, can you rank me these leaks from top to bottom, which one is more likely to happen, then I like to use ranklib. And yeah, that was it. Thank you for bearing with me. I would like this opportunity to seize this moment to say a big thank you to the data science team in dunnhumby. I think it has helped me a lot. If I'm able to be here today and talk to you about these things, it definitely has been all the experience and the learnings I have here. I particularly want to thank Richard Smith, my previous manager, and Chris Brooks, my current manager, for making also Stacknet happen. And having said that, I'm happy to take any questions.